Learning Objective A is going to have us compute the probability of simple events. So let's talk about what event is. An event is going to be any subset of the sample spaces that we just talked about in an experiment. Fair and unbiased is important. Here we want a sample space which contains all outcomes that are equally likely. If each outcome is not equally likely, then it is not considered fair and unbiased. So how do you find the probability of an event? The probability of an event, this is shorthand, it's the P means probability, E is the event. All you're going to do is you're going to do this. It's going to be N, the number of everything in the sample space, and then on the top is the number of those things in the event. So for example, if I said, what's the probability of rolling the number 2 on a 6-sided die? In that case, I might write the probability of getting a 2 as my shorthand. That would be the total number of outcomes in the sample space. Well, that's 6. How many make this event of being an actual 2? That's 1. So our probability would be 1/6. There's some key things you want to know about probability. The first thing here is that probability is between 0 and 1. It can be as low as 0 and as high as 1. It can't be negative, nor can it be higher than 1. This right here says if the event is equal to the sample space, then the probability of the event happening is equal to 1. That case might be, what if I have a deck of cards and they're all red? What's the probability of picking a red card? That would be all the cards out of all the cards, which would be 1. Point 3 says here, what if the event equals, this means null, what if the event is empty or can't happen? Let's go back to having a deck of red cards. If they ask me the probability of finding a black card in an all deck of red cards, it's impossible, so therefore the probability is 0. The first example here says, in an experiment of tossing 2 6-sided dice, list the outcome in the event of tossing a difference of 4. So you want to get familiar with the 6-sided dice. Remember, if we have 2 6-sided die, die 1 and die 2, there's 6 and 6 outcomes for each die. There's going to be 36 in total. So if I wrote this here, the probability, I'll just put that the difference is a 4. That's going to be something out of all 36 outcomes. Go back to all 36 outcomes and look at those that have the difference of a 4. If we listed those out, what would they be? Well, the difference between 5 and 1 is 4, but so is 1 and 5. 6 and 2 is 4, but so is 2 and 6. So in terms of that, there would be 4 of them, so the probability is 4 out of 36, which is fine, or if we simplify, 1/9. Now this next one here, we're tossing the 2 fair-sided die again. What is the probability the sum is 4 this time and not the difference? So now they want us to find the probability the sum is 4. Well, there's 36 possible outcomes. If we list those, the sum would be 4, would be 1 and 3, or 3 and 1. Another one that's going to work is 2 and 2. And that's it. So in this case, it's 3 out of 36, and that simplifies to 1/12. In this example, we have an experiment that consists of tossing 2 fair coins and counting the number of heads. Here it says, consider these events: 1 head in all, 2 heads in all, or 0 heads in all. Are these events equally likely? Well, if we look at the sample space, we're tossing 2 fair coins, and here we have a picture. We have, of the 2 coins, we get 2 heads, 2 tails, tails and heads, or reverse it, heads and tails. So there's 4 possible outcomes here. So for our probabilities, we can figure them out. Let's do this one, this, and this. They're all going to be at something out of 4, and we just have to see what works. So the first one, that there's 1 head in all, well, that's 1 2 times, so that can happen twice. Probability that there's 2 heads in all, this is the only scenario, that's 1. Probability there's 0 heads in all, That would be the one of having two tails, so that's 1. In this case, are the events equally likely? No, they are not. This first one is actually a little more likely. And be careful here, this slide where it says how many outcomes there are, that is not appropriate for this question. Another popular probability example deals with the gender of children. It says here, a researcher is studying the number of boys and girls in a family with 3 children. Assume that the birth and the boy is equally likely. Okay, let's list out the sample space for this and then find the probability of the 3 kids that there's exactly 1 boy. So if we're thinking about what it might look like, we have child 1, 2, and 3. The possibility of child 1 is a boy or a girl. The next is boy and girl, boy and girl. If you multiply those together, there is going to be 8 possible scenarios. So let's actually list them first. If the first child's a boy, the second could be a boy and so could the third. Or it could be boy, boy, girl, or boy, girl, boy, or it could be boy, girl, girl. Keep in mind, these 2 here are unique because this is child 1, 2, and 3. So right here, the middle child is a boy and here the middle child's a girl. So this is a unique scenario. The only other difference is, let's go and look at it. What if the first child was not a boy but was a girl? So if we had a girl, we could have the girl, boy, boy, or girl, boy, girl, 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 boy, or we could have all 3 girls. Now the question is, what's the probability that they have exactly 1 boy? And if we look at that, we're going to notice that exactly 1 boy happens here, and it's going to happen here, and happen here, and that's it. So this is going to be 3 out of 8. Now there's a second question here, this next one. Find the probability that a family of 3 has exactly 2 girls. Well, exactly 2 girls, there's one right here of 2 girls. Exactly 2 girls is there, and exactly 2 girls is there. So in this scenario, it's again 3 out of 8. What you might notice about these 2 questions, this one and this one, really are asking the same thing, but just from a different perspective.